Hi everyone, in this video we'll be presenting our paper titled Denoising-While-Completing Network, DWCNet, for robust point cloud completion under corruption. This paper was published in the Computers and Graphics Journal and presented at the 3D Objects Retrieval Conference 3DOR in London on September 3, 2025. Here is a bit of an overview for what we're going to cover for today. Introduction, related work, dataset, and technique, followed by conclusion. So let's say we've got a warehouse and it's a pretty big warehouse and it's cluttered, and every single day of the week lots of items, devices, and objects are being moved around. It's tedious for a human to keep up with, so you employ the robot assistant Baymax to go throughout the warehouse, checking the inventory, scanning QR and barcodes, but he's having a hard time moving around because he can't see some of the stuff, and no matter how many times he rescans the scene, the points remain missing. Here's another example. Can you identify and make a 3D model of this object if this was all the data that you have? Probably not. What if it's like this? Now we can see that there is a car in this scene. But how could you determine which point belongs to the car and which part is the noise? On top of that, the car is still missing a lot of parts too. So how do we deal with situations like this? The answer is point cloud completion. Point cloud completion is a task of completing a partial point cloud input so that it fully represents a 3D shape. It is important in tasks such as object recognition, 3D reconstruction, point cloud pre-training, etc. It can be done via two approaches, traditional and learning-based. Out of the two, learning-based approach is more common, and out of the sub-branches of learning-based approaches, fully supervised methods are the most common and the most promising. And as we know, fully supervised methods require a paired data for training. Speaking of paired data, in other point cloud perception tasks like object detection or segmentation, the ground truths of the paired data can be a class label or a bounding box label. But in the case of point cloud completion, the ground truth has to be a clean and complete point cloud. And it's difficult to get such a high quality reference data from real world point clouds. But it is possible to get a clean and complete point clouds by uniformly sampling 3D CAD models. Now, keeping that in mind, we have these pros and cons. Although they are highly corrupted and there is no ground truth, real point clouds are real. If we don't make progress with real point clouds, we can't deploy completion algorithms to real world applications. On the other hand, since the point clouds are clean and have ground truths, but their data distribution does not match the distribution of the real point clouds. So where's the middle ground? After reading a lot of papers to find the middle ground, we came up with the following insight. The first insight is that most of the works on completion so far are done on clean partial point clouds. But real world point clouds are highly corrupted partial point clouds. So why are most of the completion works done on clean partials and not on highly corrupted ones? This leads us to our second insight. Almost all of the current completion benchmark datasets contain little to no noise or corruption. Even the real-world datasets, Kitty and ScanNet, are pre-processed and clean before completion algorithms are tested on them. However, there's been development in improving the robustness of other point cloud processing tasks, and we have robustness benchmarks for tasks such as point cloud classification and segmentation, but not completion. And because there is no robustness benchmark dataset, there is no robustness evaluation for completion tasks, and that's a third insight. But despite this, a few works have tried to address the issue of robustness in completion. For example, Agrawal et al. Applied denoising autoencoder before completing the object, and DWCNet uses density-based clustering, and Ma et al. Apply segmentation and farthest point sampling in order to complete corrupted point clouds. But these works are very limited, and the corruption they try to address is also. Our fourth and fifth insights are related. We found that almost all denoising algorithms denoise only complete point clouds, and all the completion algorithms tend to complete clean partial point clouds. So now we have a dilemma. What can complete and denoise highly corrupted partials? How do we deal with these limitations? Simple. We change these insights into goals. So we explore this underexplored problem of completing highly corrupted partials, introduce a robustness benchmark dataset, and a robustness evaluation framework, as well as a robust completion network. So now we discuss the corrupted point cloud completion dataset, CPCCD. In order to make the first robustness benchmark dataset in the field of point cloud completion, we started small and we chose a popular completion dataset, PCN, which has only 8 categories as our base. And then we compare the partials in the PCN dataset to those in real world indoor objects point cloud dataset, scan object NN. And then we try to see if there's a pattern to the way in which the corruptions appear in this indoor environment. And then we categorize the observed corruptions into external and internal corruptions, and as well as the random combination of the two. So we applied the observed corruptions to the PCN dataset and made the first robustness benchmark dataset in the field of completion. This is what it looks like. It consists of external corruptions, internal corruptions, and a random combination of the two. And compared to other point cloud completion benchmarks, our dataset consists of a more comprehensive list of corruptions. Internal corruptions are the type of corruptions that add points from other objects or backgrounds into the sea. One such case is when there are points that belong to other objects. And the other one is when there's a background surface, like a wall or a floor in the scene. Here are some examples of internal corruptions, which disrupt or displace the points in the object scan. Dynamic jitter with trajectory represents displacement of some of the points in the object because of sensor movement. Collision by other objects is obvious from its name. There's triaxial rotation, which rotates the axes of the object, X, Y, and Z, with random angles between 0 and 10, which corresponds to errors due to sensor movement again. And then there is isometric scaling, which last but not least represents the scale variation of real-world objects. One thing that makes CPCD different from other robustness datasets in point cloud object detection and segmentation tasks mentioned above is that instead of a set level of perturbations, we have used a range of millions of multiple combinations of the parameters in which these corruptions can appear, because we are trying to simulate the randomness of real-world point clouds. And now that we have a robustness benchmark dataset, we can do a robustness evaluation. These are the criteria we considered for the robustness evaluation setup. We tried to pick at least one architecture from the different architecture types of completion algorithms, and we had to choose the ones that were trained on the PCN dataset as CPCCD is based on it. And of course, we had to choose the ones with open source codes and pre-trained models. So we tested the selected completion algorithms, which were trained on the clean PCN dataset on the CPCCD dataset. The metric we used is comfort distance, and the lower the comfort distance, the better the completion. This graph shows us that all the evaluated networks were found to be highly vulnerable to almost all of the corruptions. Almost because we found that they did well for the occlusion by other objects category, whose results matched the results from the clean PCN dataset. The worst results were observed at the randomly combined corruptions category. We also observed that the transformer-based completion algorithms, pointer, snowflake, NIC, and add pointer did better than the other older architecture types, such as folding net and grnet. Here are some qualitative results. Of course, it is expected that completion algorithms trained on clean data cannot effectively complete and denoise highly corrupted partials. We fine-tuned the algorithms on the randomly combined corruption category of the CPCCD benchmark dataset and found the following results. Fine-tuning, all of the completion algorithms showed a significant improvement, and the best results were once again observed by the transformer-based algorithms. The qualitative results show us that most of the algorithms have learned to ignore the noise and just complete the object after fine-tuning. So they don't really remove the noise, which means we need to do something beyond fine-tuning for cleaner and more complete results. Brings us to our robust point cloud completion network, DWCNet. In order to make DWCNet, we started with Ada Pointer, the best performing network on the robustness test. And here's how it works. The input point cloud is first downsampled, and the local features are extracted and combined with positional embeddings, which are then passed through a transformer encoder. The resulting encoded features are then passed through the transformer decoder, which predicts a coarse point cloud, and point proxies, which are further refined and upsampled to a complete point cloud by using a folding decoder. Testing a bunch of methods to improve Ada Pointer's performance on the CPCCD dataset, we found that the most effective way was to introduce a new module, which we call the noise management module. Basically, the idea is to use the noise management module, clean up the noisy features in the input. The NMM is a dual-path neural network that classifies features encoded by the completion network as noisy or clean by using self-attention and contrastive learning. The clean features are then passed back into the completion pipeline to predict the final complete point cloud. So the NMM has two goals. The first goal is to pull the clean features closer to the features of the actual clean ground truths in order to create a positive alignment. And the other goal is to push apart the noisy features and the clean features as far away as possible. The first of the two paths is the clean path. It's got a transformer-based module which captures long-range dependencies via multi-head self-attention, and then it has a position-wise feed-forward network which refines the features per position. Then a pre-layer normalization is applied in order to prevent feature magnitude divergence, and residual connections are used to mitigate vanishing gradients. We're trying to maximize the similarity between the predicted clean feature and the features from the clean partial. We calculate this by using a negative similarity. It's called the positive loss because it is formulated as a negative cosine similarity, which actually has to be minimized. As is a noisy path that uses multi-scale convolutions and consists of multiple parallel 1D convolutions to capture noise at different scales. One thing we notice here is that we don't have a ground truth for the noise and corruptions because noise and corruptions appear randomly in the real world. And our dataset, even though it's synthetic, has many levels of noises and combinations of corruptions, which makes it random. So the purpose of the negative loss here is to make sure that the clean features are dissimilar to the noise. The NMM learns discriminative features through contrastive learning approach by maximizing the similarity between the clean features and the ground truths and minimizing similarity between the clean features and the noisy features. Although the positive loss proved to be more impactful, removing the negative loss risks representation collapse, where the features converge to a trivial non-informative embeddings due to the absence of contrastive pressure. It's more like a seat belt for stability and prevention of meaningless learning. After training DWCNet on CPCCD, we found that it has a state-of-the-art results in all the categories of CPCCD, and it shows up to 5% improvement from Ada Pointer. Here are more qualitative results that shows us that DWCNet does better than Ada Pointer. Listed DWCNet and the other algorithms on real-world data, tables and chairs from scan object and then dataset, and we found that DWCNet performs better than the rest of the algorithms. And since DWCNet did great on the corrupted data, we couldn't help wondering how it would do on clean data. So we trained and tested it on a clean PCN dataset and found a state-of-the-art result at the time of the submission of this paper. Are some more qualitative results. Paper has got quite a few limitations. The first one is that it's got only 8 categories in CPCCD dataset, and that the corruptions represented are of indoor environments. And we find that WCNet does not completely remove all the noise and corruption in the scene, and there is no comparison with self-supervised methods. And there is also no quantitative results on real-world dataset because of lack of the ground truth. So we're going to change these limitations into future work and include more categories of objects onto CPCCD dataset, include more types of corruptions, come up with a more robust DWCNet, and compare it with self-supervised methods, as well as show some quantitative results on real-world datasets. Here are the contributions of our paper. We investigate an underexplored problem in completion, the completion of highly corrupted partial point clouds, and we provide the first robustness benchmark dataset for completion and perform the first robustness evaluation of point cloud completion algorithms. We also introduce a robust completion network that has the state-of-the-art results on the CPCCD dataset. This work is a pioneer in an area of completion of corrupted partials and or of denoising partial point clouds. So we expect a lot of growth and future results in this area, but we have to take it one step at a time. And this paper is the first step. You can find the paper, the dataset, and our GitHub repository by scanning these QR codes. Thanks for watching. See you next time.